the situation of the fifth question on today's document. You have a square loop with corners at the origin and the point A. And we want to find the forces on the four sides if we're carrying a current I in this case, clockwise direction. So we have a constant field B in the Y direction, so we call that field Bj. We could even write B vector equals B scalar times J. So let's divide the square loop into four segments, one for each edge, one for each side. Okay, we'll let L1 be the vector from here to here corresponding to this side. The current is I, so that the force would be I times L1 crossed with our magnetic field. However, in this case, L1 is in the J direction, magnetic field is in the J direction, so we have zero force. Now, not the case for L2. For L2, L2 is in this direction, so IL2 will be in this direction. IL2 crossed with BJ is going to give us a non-zero result. Now, I'll actually calculate F4 down here, but you can write that out. And you're going to end up with negative IAB times K, just the negative of what I've written here for F4. The point is that the direction, if I do L2 crossed with the J vector, I get the negative K direction. So I have a force acting downward here. Along this side, which I haven't labeled, that we call that L3 if we want, but we know that the side being parallel to the magnetic field, the current along that side is not going to give us any force. Okay, we're not going to have any force due to the magnetic field. Now for L4, we can use the right-hand rule. L4 is in the I direction, and it's actually going to be, okay, well, we have our I dl is going to be just I times the L4 vector, and we're going to cross that with our B vector. And IL4, well, L4 is A times, I maybe should write that down, okay. L4 is A times I. L2 would have been negative A times I. L1 would be negative A times J. So if we do the cross product of I times the L4 vector AI, we get I crossed with BJ. I cross J is K. So we have an upward force. Right-hand rule tells us that rather quickly. And our force is going to end up being IABK, which is very easily calculated. Okay. Now, that's the force here. The force here is going to be the negative of that. Okay. Now, if we calculate, well, next question is, what's that going to do to the loop? Well, quickly got the reply from the class. So it's going to rotate. It's going to start the loop rotating. It might not continue the loop rotating because, of course, these forces are still going to maintain their directions in the face of this field. But this will at least start a rotation. Okay. Now, if we rotate this thing about the x-axis, in other words, if we use the x-axis and somehow fix this, put an axle here and some mechanism of allowing this loop to turn one way or the other about the x-axis, what's the torque exerted by the magnetic field? Well, the torque is R cross F, where R is the vector, and I haven't depicted it, and the picture is kind of cluttered. I don't really see a good place to depict it, but the r vector would just go from the axis to this side. So the r vector would just be AJ, okay? J direction, distance A. And we cross that with the force vector, which would be F4 in this case. And I could even say that about the x-axis, that would be R crossed with F4, which is AJ crossed with IABK, giving you IA squared B times I. Now, I ask you then to calculate the torque about y equals A over 2. And it turns out that it comes out exactly the same. We can kind of make a simple argument for that. We're going to cut the thing halfway here. A over 2, y equals A over 2 would be this line. So our r vector would be only A over 2 in this direction, which would give us half of what we got here, because the r vector would be A over 2j. From here, the r vector would be negative A over 2j, and the force would be negative IABK. That would give us another 1/2 IA squared BI, and if you don't understand that, listen to it again, write it down, and verify it, or just think it through yourself without my explanation. If you do this about y equals A over 2, you get a torque here, and you get a torque here, and they add up to IA squared B times the I vector, the same as they did before. I also ask you in the problem to prove that it's a case for any axis parallel to the x-axis. Okay? If you rotate this thing about any axis parallel to the x-axis, you're going to get this. Now I'm going to use that as a introduction to the idea of the magnetic moment. So let's stay with me for a minute here. We're going to have our A vector. This is going to be our area vector for this loop. The area is A squared. So here's the area of the loop. And we multiply that by the normal vector, something you would be familiar with from vector calculus. And multiplying A squared by the normal vector gives us a vector that represents the area and gives a direction to the area. Now, the direction of the normal vector is going to be the direction given to you by the right-hand rule if you follow the current around here. Now, I'm not going to twist my arm around, but you see that in this case, that vector would be in the negative k direction. Now, I say n is a normal, should be a unit. I should have written it as unit normal. So n is your unit normal. And if we multiply a squared by n, we get negative a squared k then, because area is a squared, unit normal is negative k. Well, I'm going to pause here and correct something I did wrong in class. I wrote this down backwards, and then I wrote these arrows here. So I'm just going to rewrite this little bit down here a little more coherently and explain what I'm talking about. Okay, well now, if we do I times this A vector crossed with the B vector, well, A is A squared, negative A squared K, I times A is then I A squared K. Crossed with BJ, we get I A squared B times I, because the cross product K crossed with J is negative I, and the negative here gives us a positive. So we have this quantity IA. This is a very important quantity in study of magnetism. This is called the magnetic moment of this loop. Okay, it's the magnetic moment of the loop, and we designate that by the Greek letter mu. It's a vector, of course. Since you're multiplying a scalar times a vector, you get a vector. And we could say that then mu cross B, is what we calculated here, gives us what? Now, what's the meaning of IA squared B times the I vector? That's our torque. That's the torque exerted by this magnetic field on this loop when the loop is in this configuration. And it would be the same wherever the loop is because of what I said but didn't prove about the torque being the same about any axis. Okay, we showed that the torque is the same about this axis and this axis, and I asserted there's nothing unique about those axes. It would be the same for any axis parallel to the x-axis. Okay, the idea of a magnetic moment. Put the magnetic moment together with the magnetic field, it tells you how much twisting there's going to be.